My name is Sydney Schmidt and I'm the team lead.
Hi, my name is Ryan Smith and I'm the procurement lead.
Hi, I'm Walter Romer and I'm the optical science lead.
Hi, my name is William G. I'm the mechanical engineering lead.
Hi, my name is Zachary Steinberg and I am the aerospace lead.
We are Project 24027, the RDE Aerospike nozzle optimization team, and the goal of our project was to design and optimize an Aerospike nozzle to be fitted on a rotating detonation engine to achieve a greater level of fuel efficiency. Rotation detonation engines are a new type of engine that supersonically burns fuel and oxidizers to produce a greater fuel efficiency than a conventional combustion engine within a smaller form factor. RDEs provide the possibility for a large increase in thrust compared to conventional engines. However, they are subject to efficiency losses at changing back pressures. An Aerospike nozzle is a type of rocket engine nozzle design that is characterized by a protruding spike-like structure at the center of the exhaust opening. This design is intended to improve engine efficiency over a wider range of altitudes compared to traditional bell-shaped nozzles. An Aerospike nozzle will produce an increase in thrust as well as reducing efficiency losses at different back pressures caused by different altitudes. And when combined with an RDE, this could lead to even greater overall propulsion efficiency.
So here we have the RDE that we'll be using for our that we used for our project. As you can see, we're looking at it from a top-down view, so you can see into the chamber. Right now, it's missing the inner wall, which is this piece right here, but you can imagine that's slotted right in the middle there. Around the outside, you have a number of things. These three are pressure transducers. That's what we're using to track the pressure wave as it goes around the chamber. And then we've also got this input port right there, which is very important because that's where this goes. This is our detonation igniter. It basically forms a detonation wave that propagates along this tube and enters the chamber to begin circulating around. Now, the way this engine works is just like any other rotating detonation engine. You have a spinning rotating detonation wave around the outside. Now, the detonation wave produces a very high efficiency combustion, but also introduces some challenges that we're here to work with. So the main challenge is that the detonation wave is highly transient and it spins around the chamber. When it exits the chamber, that means that apart from the axial flow that you would expect from a rocket engine, you also get a pretty significant tangential flow that can lead to a loss of efficiency during the in a normal engine nozzle. So one of the main goals of a nozzle specifically designed for a rotating detonation engine is to correct that axial flow and get it straightened up to go axial again.
These are our system requirements. First, for performance, the system shall produce a thrust coefficient greater than 1, survive a 5-second burn, retain performance over the burn time, and have no increase in throat area after the burn is completed. Second, for environmental, the Aerospike will interface with the rotating detonation engine, perform at ambient temperatures and pressures. Third, for safety, non-hazardous oxidizers and fuels will be used. The ambient pressure will also be greater than the exhaust pressure. Lastly, for design features, the Aerospike will be mounted with a central master screw. The system will use hydrogen gas and ambient air for fuel and oxidizer, and the system will also use multiple mounting screws around the circumference of the RDE.
So here's our starting point. It is a simple 3D printed model of a nozzle based only on area expansion. We've got a spike which includes the choke and the curve, and then we have a lip which shortens, which sort of fits conformally around the spike right there. The ones we actually made and tested out of stainless steel, we have the lip right here, which provides just a flat sort of lip around the outside of the engine, and then we also have our nozzle, which provides the shape, and our choke plate, which provides the choke, and these are separate.
All right, so here we have our different configurations that were used for testing with our rotating detonation engine. Here we have the standard inner wall that does not choke the flow at all. Here we have the basically choke plate, which is the same as the inner wall with a choked flow. And then here we have the Aerospike nozzle itself. So for our testing, we put the inner wall and the choke plate by themselves in the rotating detonation engine, and we also tested each of them with the Aerospike nozzle on top of them. Now, for all of these tests, we also did them again with this outer lip that goes on top of the choke plate, which helps choke the flow even more. And everything was held in by our master screw here.
Pictured here is our complete setup that we tested at R3 Aerospace in Marana, Arizona,
we used air at about 900 psi and gaseous hydrogen at about 500 psi. This is me working on the rotating detonation engine, getting it ready for its test, and also a picture of it with the Aerospike nozzle on. Next up, you guys will get to see our thermal imaging video from the actual test.
Stop. Data log. Restart. 3, 2, 1.
Looking at our test data, the two main variables I looked at were chamber pressure and force. There are two example plots here shown of the chamber pressure versus time, as well as the voltage versus time, that were gathered during our test. The most important thing to note here is that the load cell gives force output and voltage, so it needs to be converted to pounds in order to be useful. So in order to calibrate the load cell, we had to determine a relationship between volts and pounds. To do this, we used a series of data points to find a linear relationship. The first one was that when there was 0 pounds of force, there was 1.25 volts because of the offset voltage. The next point came from the fact that we calibrated the load cell before testing with a 40-pound weight on top of a 44-pound engine setup, so the total weight was 84 pounds. When doing this, the load cell measured 1.49 volts. The last point came from calculating the full-scale output. The load cell's max force is 220 pounds, so using the formula for output voltage, the output is 1.9025 volts. I then plotted these on a graph to identify the relationship. Looking at the graph, I added a line of best fit to the 3 points and came up with an equation. I then used a linear equation to find the corresponding force in pounds for the output voltage given by the load cell. For example, when we got a voltage of 1.53 volts, I plugged that into the equation to get a force of 95 pounds. In order to find the thrust coefficient, we used the following equation. Thrust equals the chamber pressure times the throat area times the thrust coefficient, and then solve for the thrust coefficient. As I said previously, we got the chamber pressure and thrust in the test. We also know that our throat area is 1.814 inches squared. Here is a sample calculation using the test data, where we found the coefficient to be 1.28. Before we could fully find the thrust coefficient for each test, we had to calculate the average chamber pressure and thrust values. To do this, we wrote a MATLAB program to read the data file and extract the column of data that we wanted. After this, we can finally find the thrust coefficient for each trial. And here's a table of our thrust coefficient results. We had 8 different tests, with the first one being used as a trial to make sure the login was working. The configuration for each test is shown below, along with the air and hydrogen PSI level. For certain tests, we had more than one firing, which is denoted by the different files. Looking at the results, we'd expect the highest thrust coefficient to be with the choke, spike nozzle, and lip configuration, which it clearly is. Overall, the tests were a success because we were able to achieve a thrust coefficient of up to 1.33, which means the Aerospike nozzle amplifies the thrust because it is greater than 1.
With further research and development, integrating Aerospike nozzles with RDEs can have a notable improvement in propulsion efficiency. It can optimize thrust across a range of altitudes and have the potential for reduced fuel consumption and lower operational costs.